Hello friends. So after covering a couple of numericals on inverse Laplace transform using shifting theorem, we are going to see one more numerical. Now in this guys, our denominator is a degree 4 equation. So let's see how to evaluate such function and how to get the inverse Laplace transform of that by using shifting theorem. So here we have to find out Laplace inverse of s upon s raised to 4 plus 4a to the power 4. Now guys, if you see the denominator, it is s to the power 4, it means degree 4 equation. And whenever we have degree 4 equation, let me tell you that if you remember all the properties or all the formulae of inverse Laplace transform, then we do not have degree 4 equation in any of the formula. So it means if I want to get the answer or the inverse Laplace transform of this function, then I should bring the quadratic equation in the denominator at least. So to get that quadratic equation, we have to do few adjustments over here. So what we'll do here is, so if you observe the first term, it is s to the power 4 and the last term is a constant. So here one term is constant, one term is having the variable s. So guys, here this is a function of s. So s is our variable and a is a constant. So what is the adjustment that I'll do? So guys, I will add middle term in this and I will try to convert it in the form of a plus b the whole square or a minus b the whole square. So let me tell you that formula. So guys, you all must be knowing that a plus b the whole square is nothing but a square plus 2ab plus b square. Now if I want to bring this denominator in this form, then this first term a, it is the square root of this first term. So let's say if my first term is s raised to 4, so here in the bracket my first term will be s square. So s raised to 4 equal to, next let's say this last term is my 4a to the power 4 as a constant. So this second term is a square root of this last term. So if the last term is 4a to the power 4, then this term is 2a square. So guys, if I expand this, then that will become s to the power 4, last term is 4a to the power 4 and the middle term is 2 times first term into second term. So first term is s square, second term is 2a square into 2 will become 4 times a square s square. And guys, for this reason I am gonna add 4a square and s square in this so that I can get this formula. But we know the mathematical rule that if we are adding some term in the given function, then we have to subtract the same term so that we will get the neutral result or the original result. So guys, that is why I will add and subtract 4a square s square from the denominator. So here we'll say therefore L inverse of s upon s to the power 4 plus 4a to the power 4 is equal to Laplace inverse of s upon, here we will get s to the power 4 plus 4 times a square s square plus 4a to the power 4. So here I have added that term. Now I'll subtract the term, so that will become minus 4 times a square s square. Now guys, here if you will see first 3 terms, then these 3 terms are matching with this formula, so I can substitute this formula over here and that will become Laplace inverse of s upon, here s square plus 2a square the whole square minus, now here I can convert it into a square term like 2as the whole square. So guys, now in the denominator I got a form a square minus b square. So we all know the formula that a square minus b square is a plus b into a minus b. So we have to add these two terms and then subtract these two terms. So we will get it is equal to Laplace inverse of s upon first term will be s square plus 2a square plus this. So plus 2as plus 2a square. So this is the addition of this two term. Now we'll subtract this two term. So s square as it is, I'll subtract this term first. So negative 2as plus 2a square. So here we have added this term and then we have subtracted this term. Now guys, to get the L inverse, I have to find out L inverse of this function. So here in the denominator there are two functions, both are quadratic multiplying each other. So it means to get the L inverse, I cannot apply inverse Laplace transform directly because there are two terms, they are multiplying each other. So linearity property is not applicable. So for that we should bring these two terms in such a form that we should get plus or minus sign between these two functions. And to bring that plus or minus sign, guys, I have to perform here partial fraction, because by partial fraction we can convert such functions or such big terms into small terms with plus or minus sign in between. So let's start with partial fraction. So before proceeding to partial fraction, let me tell you that you can get partial fraction by few adjustments also. So guys, every time doing the partial fraction is not recommended because it is a time consuming process. So if it is possible to find out the partial fraction of given function by doing the adjustment, then it is always recommended. So guys, here I can do few adjustments which can give me partial fraction of this function directly. So let's see how to get there. And you must be remember that in my previous videos I have used that method. So if you want to be perfect in that adjustment method, then you have to watch all my previous videos so that you will know how I can find out the partial fraction or how you can find out the partial fraction without performing the partial fraction process. So let's see how to do that. So guys, here let's write down that as Laplace inverse of, now these two terms, in the denominator I want these two terms and numerator I just want s. So guys, what we'll do is we will write down these two terms there by separating them with plus sign or minus sign. So here we'll say, let's say first term is 1 upon s square minus 2as plus a square, or I would say 2a square. So what I did here is I have taken the second term and let's say this second term is 1 upon s square plus 2as plus 2a square. Now guys, observe carefully. Let's say if I put plus sign here and if I do cross multiplication, then I should get this term back, but we are not getting, because if I put plus sign over here and if I cross multiply, then here we will get s square plus 2as plus 2a square. Here we will get s square minus 2as plus 2a square. It means only 2as and negative 2as will be cancelled and we will get s square plus 2a square, and from here s square plus 2a square. But in the numerator actually we just want s term. We don't want s square term and we don't want 2a square term. So that is why guys, I'll put here negative sign. Because by negative sign what happens here, if I cross multiply, here I'll show you in the rough. Let's assume that this is a rough part. So by cross multiplication here we will get s square plus 2as plus 2a square, and by this cross multiplication we will get minus 1 into this, that is minus s square plus 2as minus 2a square upon multiplication of these two brackets. Now guys, here s square and s square cancel, 2a square minus 2a square cancel, and here we can get 2as and 2as 4as. But in the numerator we just want s. I don't want 4as. So to remove that 4a, I will divide by 4a. So if I divide by 4a, 4a and 4a cancel, we will get just s in the numerator. And guys, here we got the partial fraction. So without actually performing partial fraction, we got the answer. So guys, this is how we can get the value of partial fraction by doing few adjustments. So I'm sure that you understood this process. So now I'll move ahead. So here we can see that 1 upon 4a is a constant because it does not have any s term. So I'll take that 1 by 4a outside, and then I will apply this inverse Laplace transform on these two terms separately. So again, if I apply this inverse Laplace transform directly on these two functions, then we know that we cannot find out inverse Laplace transform directly because it is not at all matching with any of our standard formula. So guys, what to do? So for this reason, we will convert these terms into our standard formula, and that is why here I will adjust this last term. So see here what I get. So here I'll write L inverse as, or inverse Laplace transform of, s square minus 2as, and this 2a square is a square plus a square. Now guys, by doing this, if you observe these first three terms, then these three terms are the expansion of s minus a the whole square. So similar thing I'll do here. So for that, what I'll do, I will divide this 2a square as a square plus a square. So here we'll get s square plus 2as plus a square plus a square. And again these three terms will give us the same form with plus sign in between. So guys, here next step will be 1 upon 4a Laplace inverse of. Now guys, you must be thinking how I got this form from these three terms. So for that you have to revise, or you have to go through my previous videos, because there I have explained you that process. Still, I'll take it for you. So to get this term, we always take square root of first term. So square root of s square is s. Then we take sine of second term, which is negative, and the square root of third term, that is a. And guys, here I got the same result. So if you expand this, you will get this again, plus a square minus 1 upon, let's repeat the process, square root of s square is s, sine of second is positive, square root of third term is a, the whole square, plus a square. Now guys, if you see this first term, then it is a function of s minus a, because now we don't have s. In that whole function, we have s minus a everywhere. So now it is not the function of s, it is a function of s minus a. Similarly, this second term is a function of s plus a. So guys, here I am gonna use the shifting theorem. So let me show you that according to the shifting theorem, we should have Laplace inverse of phi of s plus a or a function of s minus a, and we got the same function. And guys, the answer of this is nothing but e to the power minus at into Laplace inverse of phi of s, where we get phi of s by replacing s plus a with s. So let's do that. So here that will become 1 upon 4a. Here it is in the bracket, s minus a is there. So if it is s minus a, this will become e to the power positive at. So e to the power at into Laplace inverse of, here answer is phi of s, and to get phi of s, we replace this s plus a or s minus a with s. So here I have s minus a, I will replace that with s. So that will give me 1 upon s square plus a square. Minus, now let's find out Laplace inverse of this function. So again, here this is a function of s plus a, that will become e to the power minus at, and Laplace inverse of 1 upon, let's replace s plus a with s, so this will give us s square plus a square. And now guys, it's the last step. So what is the value of this Laplace inverse of 1 upon s square plus a square? So I'm sure that you have gone through my previous video, that is formula of Laplace transfer, and formula of inverse Laplace transform. So I'll use that formula directly. So this will give us 1 upon 4a e to the power at, and inverse Laplace transform of this function is 1 upon a sine at. So this is 1 by a sine of at. Similarly, here we will get e to the power minus at 1 by a sine at. Now guys, from these two terms, I'll take 1 by a common and sine at common. And guys, now if you see this bracket, then you must be remember some formula. So it is matching with the Euler's formula. So if I divide this by 2, then it is nothing but the formula of hyperbolic sine at. And for that reason, I'll divide this 4 into 2 parts. That is 2 into 2, and I'll take 1 2 inside here, so that here I'll get the formula of hyperbolic sine at. So this will become 1 upon 2a square sine at as it is, and 1 2 will go inside, will divide here, and that will become hyperbolic sine of at. And guys, this is nothing but inverse Laplace transform of given function. So I'm sure that you understood how I converted that degree 4 equation into a degree 2 equation, and then how I got the inverse Laplace transform by using partial fraction and shifting theorem. So guys, if you want to learn more videos on Laplace transform, then keep watching my video. Also, you can recommend it to your friends so that they can also get benefited through this explanation. Thank you very much.